mean free path. So we've been talking about how molecules travel in a straight line until they run into something. The average distance that a molecule can travel before it runs into something is called its mean free path. Mean here does not mean that it's unpleasant or cruel or anything. It's just more like average, right? Median. So the average free path. As the pressure increases, the particles are going to be closer together, and so the mean free path is going to get smaller. So here we've got this illustration of these gas particles, and here's the one, red one, and you can see as it goes along, it's bouncing off of various things, right? And so the length of each of these red line segments, that would be the free path length. And so if you took all of those and averaged them together, that would give you the mean free path. Sometimes it's short, and sometimes it's longer. So just to give you an idea of the how long that is relative to their size, if nitrogen was the size of a golf ball, it could travel about 40 feet before it collides with something. So that's quite a long ways. So we know that gas molecules spread out from high concentration to low concentration. And here's where you can tell I'm a boy mom. I've got 5 sons. This makes me think of farts. Boys fart a lot, at least my kids did. So let's pick on this corner since nobody's actually sitting up there. What if somebody is sitting up here and they let this big old fart, right? And it's a stinky one. Right? So the people in the far corner, are they going to smell it immediately? No. It takes a while, right? The people that are closer are going to smell it first, right? Oh, man, what did you eat, right? But it's gradually going to fill the entire room, right? Because the stinky part of the fart is a gas. And like all gases, it's going to just expand to fill the room. Now, it won't be as concentrated as it was originally over there in the corner, but it's going to spread out. How do gases spread out? It's called diffusion. So gas molecules spreading out from high concentration to a low concentration is called diffusion. Heavy particles will travel more slowly, right? Average kinetic energy. Heavy particles travel more slowly. Light particles travel more quickly. There's another related concept called effusion. So there's diffusion and effusion. Effusion is the process by which a gas escapes through a small hole into a vacuum. The rates of diffusion and effusion are both related to root mean square velocity of the gas. So if we're looking at gases at the same temperature, the rate of gas movement is inversely proportional to the square root of its mass. So bigger particles move more slowly, smaller particles move more quickly. This is Graham's law of effusion. So this is an illustration of effusion. So originally all these blue gas molecules were in this side of this container, and there was a vacuum over here. A vacuum is not the thing you clean the floor with. It's the absence of anything, right? There were no particles in here, perfect vacuum. And then there's this little hole, and there's a whole bunch of gas particles over here. It's a little bit like a balloon, right? So we know that regular latex balloons, they're going to go flat. They're going to get smaller within, a day or so. How does that happen? The gas particles are coming out of the balloon. How are they doing that? There's little teeny tiny holes in the latex. You can't see them. Well, how does it hold the air at all, or the gas? Well, there's a lot that isn't holes, but it's a little bit like this. So here's that little tiny hole in the balloon, and here you've got all these gas particles under pressure. What are they doing? They are traveling in straight lines until they run into something. If someone has a direct path collision with the hole, it will go through. Otherwise, they're just bouncing around in here. This is not at all how I imagine it working, right? I would think that the pressure in there is squeezing the molecules out of the hole, right? It's pushing them out. But gases don't act like liquids. They're not getting pushed out. They're just zinging around until they happen to hit the hole. Then they'll come over here and continue bouncing around until eventually somebody might hit the hole and go back to the other side. So what's going on here? The rate of effusion is how fast this gas moves from this side to that side. And so we look at the ratio of rates of effusion for two different gases. We're not going to be calculating absolute rates of effusion because it's not really very meaningful at all. The rate for gas A divided by the rate for gas B is equal to the square root of the molar mass of B divided by the molar mass of A. So the rate for A is larger when when its mass is smaller. So helium will escape from a balloon faster than air because helium atoms effuse faster than nitrogen molecules. Air is mostly nitrogen, molar mass of 28. A helium balloon has helium in it, mass of 4. So, this is something, a little science experiment you could try at home. 2 latex balloons from the same manufacturer, fill one up with air and one up with helium to the same size, and just see what happens over the course of a few days. The helium balloon will get smaller faster than the air balloon. The holes in the latex are the same size. The pressures were the same size pressures were equal when you started. But because the helium molecules or atoms are smaller, they're moving faster, and when they're zinging around faster, they have more chances to hit a hole and escape. That make sense? So, there may be a question on the exam like this. Find the ratio of the effusion rate of hydrogen gas to that of krypton gas. So the rate of hydrogen, let's call that rate H2, and the rate of krypton we'll call rate Kr. I think one of the hardest things about these problems is figuring out what the question's really asking us to do. So it wants the rate of hydrogen to krypton. The ratio of hydrogen to krypton. So that would be the rate of hydrogen divided by the rate of krypton. So that's going to be equal to, over here we have a ratio of molar masses, but it's inversely proportional. So rate of hydrogen is on the top here, the molar mass of hydrogen is on the bottom, and the molar mass of krypton is on the top. We don't know what either of these rates are. Those rates would depend on the temperature. They didn't tell us what that was. But the ratio of them is dependent on the ratio of their molar masses. So again, this really should be in kilograms, moles per kilograms per mole. But if we have kilograms per mole divided by kilograms per mole, the kilos could cancel out, and we're going to get the same answer if we have grams per mole instead of kilograms per mole, because it's the ratio, and the exact unit doesn't matter. I'm just going to go ahead and stick with the kilograms because I don't want to make things unnecessarily complicated. What's the molar mass of krypton in kilograms per mole. Yeah, gosh, I cannot see that part of the periodic table. So it'll be 0.08380. 0.08380 kilograms per mole. Because in grams, it's 83.8. And for hydrogen, it's going to be 0.00202 kilograms per mole. And then the square root of that. .44. Yeah.
The KR on top of the H2.
That's a good question. How do I know to put the molar mass of the Kr on top of the H2? Because this needs to be opposite of this side.
Okay, so then how would you also know?
So how do I know to put the H2 on top here? Because the problem is saying the ratio of this to that.
Okay.
So the one goes on the top and the two, the other goes on the bottom. So then when I get an answer of 6.44, that tells me that the rate of hydrogen is 6.44 times faster than the rate of krypton. Okay? Yeah?
Do we have to change it to kilograms per mole?
No, you don't. No. Because that conversion cancels out. Yep. So 6.447 to 1